All right, so 7.3 is on the simplified form of radicals. So a radical is considered simplified if the radicand can't be further simplified, meaning there's no perfect squares or perfect cubes or perfect to the fifth powers or whatever the index would be. It also means that there's no fractions under a radical sign and that there's no radicals in a denominator. So we do this process called rationalizing the denominator in order to meet this last criteria. With the fractions, we end up taking the square root or cube root or nth root of both the numerator and denominator. And if the denominator is still then a radical with it, then we rationalize it. So we'll see that as we go through here. So a couple important rules for radicals. When you have a root of a product, you can break it up into the root of each of the factors. Please note that that is different than if there's a plus or a minus. You cannot break up over a sum or difference only for products, only into factors. So this works. Similarly with division, you can do the nth root of your numerator and then the nth root of your denominator. Sometimes you can simplify the fraction and then take the nth root of that. It just depends if it goes, b goes into a evenly or not. And then a rule that we saw earlier is that a square root and a square essentially cancel out. However, in this case, it's for an a that we don't know if it's positive or negative. So if you took a, let's say 9, and you squared and got 81, and then you took the square root, you'd be back at 9, positive. If you took negative 9, and you squared it and got 81, and then you took the square root of that, you'd end up with 9. So you're always ending up with a positive, whether you put in a positive or a negative. I just did it with 9 and negative 9, but here I have this example worked out with 5 and negative 5, and you'll notice it's always giving you a positive 5 as a result. So in the case when we know it's a positive, then it just cancels. And in the case where we know it's a negative for our radicand, we would know that when we cancel these out, we're left with a negative. And we saw that before when I had in the prior lesson, but now it's a little bit different because we have an A and we don't always know what A represents. So that's where we have to put absolute value bars around it when we don't know. For a cube root, when it's a positive going in or a negative, then it will, no matter what, give you back what you put in. So like 2 to the third, the 3 and the cube root cancel, just 2. 3 and the cube root cancel here. Third power and the cube root cancel here, because when I do the negative 2 to the third, I get a negative, and when it's an odd index, it's a negative. So whenever you have a negative with an odd, you're good to go. It'll be a negative. When you have a positive and a odd, you're good to go with just a positive. So if we don't know what it is, for the index, for the radicand, we don't know if the A is positive or negative. Well, it's just whatever the A is. We don't have to worry about the bars when it's a odd index. So this rule that I've highlighted is very important. So to generalize the even case and the odd case for your index, here is the generalized rule. So when you're taking an nth root of something to the nth power, you want to put bars around it if n is even. And you don't need to worry about that and in fact don't want that when n is odd. That's only when the sign of your A is unknown. If you know what it is, then you just have to follow the rules from prior lessons. For example, if I look at, let me find a better example. Here, the cube root of negative 125, I know that's going to be a negative. There's no question about that. But when I have x's or m's, I don't know if they're positive or negative. So let's work on some simplifying of radicals. So unlike the prior examples that I did in the last lesson, we're not dealing with perfect squares or perfect cubes, perfect nth roots. We have here the square root of 75. If I type that in my calculator, it'll say 8.660254038. That is an approximation of the square root of 75. I know that the square root of 75 would definitely be between 8 and 9 anyways, because it's between 64 between 8, which is 64, and 9, which is 81, because 75 is between 64 and 81. But in order to get it simplified, I had to pull out any of my, in this case, square factors. So there's a square factor of 25, and this is 25 times 3 is 75. And so by pulling out my square factor, because I'm taking a square root, I'm going to get my integer, 5, and then my other factor, I still have to take the square root of that. So that's considered simplified because there's no more square roots. There's no more square factors underneath the square root. There's no fraction in the square root, and there's no square root in a denominator position. So how can you do the 75? Well, a couple options. You can either know your perfect squares and put your perfect square times whatever the other factor is. Or if you're not sure, you can use a factor tree. I ended up doing 5 and 15 because I saw it ended with a 5, so I knew it was 5 times something. You might have known that it goes 3, 3 times 25. That's fine too. The ends of your branches are always your prime numbers, and they're always then your factors that multiply to your original number. So I'm looking for something that has a square root, groups of 2 of something. That's the square root. So I found a group of 2 5s. So I can pull out a 5. So in other words, I think of it as the pairs get pulled out, and then the leftover part gets left under the root. Since it was a square root, this is going to be a square root. Here you can see I had two 2's, and here another 2 2's. So it would be a group of 2 here, a group of 2 here, and a leftover 3. And then I can simplify that to 4 root 3. Here I thought of it as a perfect square, 100 times 2. So I got square root of 100 is 10, square root of 2 is square root of 2. If I did my factor tree, I'd have 5 times 2, and then a leftover 2. And notice I kind of circle my ones that I'm pulling out, the ones that I'm looking for groups of 2 of, because I'm doing the square root, and then the leftovers I box. That's just a way I keep track of it. So 40, you might think of it as 4 times 10, or 2 times 20, or 8 times 5. Keep going until you get to your prime numbers. You'll end up with 3 2's and a 5 at the ends of your branches. This time we're looking for groups of 3. We're looking for cube numbers. So here it is, 2 times 2 times 2, that's 3 2's. So this is like saying the cube root of 8 is 2. And then we're left with the cube root of 5. So you could add in here this idea of it being, let's go not to yellow. The cube root of 8. Wow, this pen is not working out so well. Cube root of 8 times 8 times 5. And so then the cube root of 8 is the 2. And then the cube root of the 5 is the cube root of 5. Let me erase that. It's pretty messy. Okay, so this next one, when I did it with 80, and I'm looking for groups of 4. I had 4 2's, so I can bring out a group of 2's. That would have been a 4th power of 16, and then times 5. So 16 times 5 is 80, 16 being the fourth root, having a fourth root of 2, and then the leftover 5. Just make sure you're putting in the index. That's one of the most common mistakes on these, is getting so used to just the square root that we just accidentally say 2 and then the square root of 5, which is definitely different than 2 times the fourth root of 5. So make sure you're paying attention to your index. All right, so now it's some variables. So we can deal with the numeric part by, again, breaking up to perfect square and something else, or doing a factor tree, and we'll determine that we have 5 and then a root 2. And then we can look for things that are squared, because then a square root can cancel out. So I can think of 8 as what? 4 squared, because you multiply when you have a power to a power. M squared, and then another m, that makes m to the third, and then y. And so when I take this square root, those cancel. I'll have the 2 is left under. Here, these 2's cancel, so I'll have x to the fourth out here. These 2 in the square root cancel, so I have an m, but then I have an my left over also. And again, the index is invisible 2, so that matches. The other option, besides writing it with things that are powers of 2, is to say 8 divided by 2. Remember that exponent divided by the index? 8 divided by 2 is 4. 3 divided by 2 goes in one time with 1 left over. 1 divided by 2 doesn't go in at all, so it's just all left under here, just the y right there. If we assume positive variables. If we don't assume positive variables, if we don't assume the x, and the m's, and the y are positive, then you would need to put your absolute value bars around what you pull out. However, x to the fourth is a positive anyways, so you don't really need to worry about the bars on that one, because to an even power, it's always going to be positive. But you can put it if you want. But then this m definitely needs to be put around bars if we don't assume positive variables. So that's kind of the distinction. You have to read the directions. Most of the time we are going to assume positive variables, but occasionally, to really test and know the rule, the property, we'll have you not assume positive variables. Here's 24 with a factor tree. We're looking for groups of 3 again of some factor. We have 3 2's. So I can pull out a 2, left over gets left under. And when I do these, I typically like to start with my numeric part, and I leave a gap for any of my variables, and I put my index in and make sure it looks like an index and not an exponent of the prior factor, or that it looks like a coefficient. You want it to look like the index. And then you put in your leftovers as you go. So then when I look at the m, 2 divided by 3, well, it doesn't go in, so it's all stuck in here. I didn't have any groups going out. You can see there's just 2. They're both leftovers. I have a box around them because there aren't 3 of them. For w's, I didn't draw it out, I don't think. No. But imagine if I had 15 of them and grouping them in 3's, I would end up with 5 of them, no leftovers. So there's w to the 5th. And then no w's left over. This pen is really hard to use. Okay, and then for r's, you can see I drew out 7 of them, groups of 3, because that's my index. So I had 1 group of 3, another group of 3, so I have 2 groups of 3. So I get r times r squared out here, and then I have 1 left over. So then I put r squared and r. And then I go on to s's. 32 divided by 3 goes in 10 times, makes 30. So there's the 10 times with 2 then left over to make the 32. And then here we have 3 divided by 3 is invisible 1, You don't need to put it, it's invisible. That's okay that it's invisible because x means x to the first. And I wouldn't have any leftovers. All of them got pulled out. There's no leftovers. There'd be none in boxes. And again, I'm trying to circle groups of 3 because the index was 3. And let me erase that stuff now. Okay. And here it says don't assume. So when I take out this variable, I need to put bars around it. Again, don't forget your index. 7 divided by 4 went into 4 one time with 3 leftovers. For B's, for the 32, there would have been 5 2's multiplied out. I took a group of 4 of them for this 2, and the 5th one is left over here. So these are similar questions, except I changed the exponent here so you can see if it goes in evenly, if some come out and some are left over, or if none come out, how that all works. And then here, cube root and a cube power cancel. Here we can think of this as a perfect square, so then you can see the square and the square root cancel. Do not take the square root of terms, only factors, so you cannot split it up like this. Remember that rule I mentioned earlier. Was it this lesson or the prior lesson? I think it was in the prior lesson. All right, so then some arithmetic with some division really with these. Root 20, you simplify your root, and then you can simplify your fraction. So here would be 3 times, this is 2 root 3, divide by 8, you can simplify. So a bunch of examples with simplifying your root and then simplifying your fraction. Here, simplify the root, and then both of these could be divided by 2, so you get 4, and then 5 root 3 over 2. That's not as friendly, although it is equivalent. This is the nicer way of writing it, because 8 and 5, the coefficients of the terms, don't both go into 2 evenly. We just leave it like that. And then a common mistake that happens is students go, oh, I can add 8 and 5. And so then they want to say 13 root 3. But now you've changed addition just to multiplication. In other words, you need to multiply this before you add because of PEMDAS. And multiplying this, it's not a pretty scenario. It's a irrational value. Root 72, 6 root 2. Now both of these coefficients do go into 2. And I'm looking at 10 and I'm looking at 6. Because I have 6 of these root 2's. If I divide by 2, I'll have 3 of the root 2's. And 10 divided by 2 is 5. And then this, as I just said, would be 6 root 2. You do not take half of the root. It's about the coefficient, not about the radicand. Here is another one where we have a square root in the denominator, which I mentioned earlier was not considered simplified. There's 3 ways that you can do some of these, and some of them you can only do one of these ways. So in this case, I can think of this as the square root of 8 divided by 2, which is square root of 4, which is 2. We're not always that lucky. You can also do it like we just did a moment ago, simplify your root, and then see if something cancels. And if the roots cancel, well, you're good to go. That's simplified. This top version is the generic method because it's going to work in all cases to get rid of the root in the denominator. This is called rationalizing the denominator. Let's see. And so what you do is if you're basically trying to get rid of a square root, so you're going to need to square, you're going to need to multiply it by itself. But if you multiply by root 2 in the denominator, you'll need to do that in the numerator to not change the value, because again, this is like saying 1. So I'm not changing the value when I multiply by 1. But by doing that, by essentially squaring, we can say, well, that's the same as square root of 4, which is 2. Or we can say it's root 2 being squared, and the square root and square cancel, it's 2. So no matter how you handle this denominator, it's 2. And then the same rule that we saw earlier, we often use to break up 8 into like 4 and 2. We can also go the other direction. If you have a root with an index of 2 and another root with an index of 2 that are being multiplied, you can multiply the radicands. So you'd have root 16. Root 16 happens to simplify, and then I can simplify my fraction. And sometimes you'll get a problem where this doesn't simplify, and you're able to get the rational, the non-root in the denominator by this process. So you'll see that as we continue on. Number 18. Number 18 is the cube root. So we can take we can't really do much with 16 and 125. So we can take the cube root of the numerator and the denominator. This happens to be -2 cube root of 2, and I see I have 3 2's. That means I can bring a 2 out. The negative with an odd means a negative there. So this gives us the -8 times a +2 will give us that -16. So the leftover is 2. And in the denominator, we end up with 5 and then 12 divided by 3, so m to the 4th. So now we've rationalized it because there's no more root down here. Now we haven't done it by the process of rationalizing. It's just in our simplification, it became rationalized. And then here is an example that you'll see more when we get to quadratic formula. It's just practice on really order of operations and simplifying roots here. So you do your multiplication and your exponents, then multiplication, then you finally get to do your addition or subtraction, and then you evaluate your root. And so you get 2 root 15 on that one. So that is 7.3. And that's it for right now.